Hello again. This is Math 1431 coming to you from the College of DuPage. And the title of this lecture is Principle of Mathematical Induction. As always, please be attentive listeners while watching this video. By way of introduction, the principle of math induction is much like knocking over a bunch of dominoes. There really are two things that happen to knock over a finite set of dominoes. The first thing is you have to knock over the first domino, and you'll see that that's analogous to the case where n equal 1, or knocking off the first domino. But then all of the dominoes must be positioned such that when this one falls, it knocks over the next one, and so on and so forth. And that is equivalent to the induction step. Now, many people have world records for these dominoes in terms of configurations and number that they knock over, but they're always knocking over a finite number. You see, our goal is much loftier. We seek to prove things for all n greater than a fixed integer, an infinite number of cases. So let's begin then. Math induction is a powerful and elegant technique for proving certain types of mathematical statements. General propositions which assert that something is true for all positive integers or for all positive integers from some point on. Let's look at some examples of the type of results that can be proved by induction. And we'll talk about two propositions. Proposition 1, the sum of the first n positive integers, 1, 2, 3, is n times n plus 1 divided by 2. The second proposition is a geometrical one. It says in a convex polygon with n vertices, the greatest number of diagonals that can be drawn is n times n minus 3, all by 2. Now, I'm going to talk a little bit about what it means to be a convex polygon. So a polygon is said to be convex if any line joining two vertices lies within the polygon or on its boundary. And so you can see that this is convex because that statement is true. This is not convex because if I join this vertex with this vertex, the line joining those is outside the polygon. So as you can see, the subject matter of the statements that we can prove by induction can vary widely. It can include algebra, geometry, graph theory, and many other topics. What is common that all the examples is that there's a number n that appears in the statement. In all cases, it is either stated or implicitly assumed that n can be any positive integer. And I note in passing, although we won't do examples of this, we can even prove inequalities this way. Now, I'm going to back up just a little bit before we prove those propositions, and I'm going to say, why do we need proofs by induction? So let's look at another example to see this. Suppose we were trying to prove a proposition, which will turn out to be false, but the thing that we're studying is if p is any prime number, 2 to the p is also a prime. And if we start checking some cases, we will see that it works for 2, it works for 3, 5, and 7. So since all those numbers are primes, we might be satisfied the result is always true from this inductive sample. But if we try the next prime, which is 11, we find that 2 to the 11th minus 1 is 23 times 89. So it's not a prime, and our general assertion is therefore false. Now, we're going to turn our attention to proposition 1 and ask how many cases will we need to check before we could say for certain it is true. Well, imagine you get a computer on the job and set it to the task. No matter how many values of n we find the proposition to be true, we could never be sure that there was not an even larger value for which it was false. This explains the need for a general proof which covers all values of n. Mathematical induction is one way of doing this. One way of thinking about mathematical induction then is to regard the statements we are trying to prove as not one proposition but a whole sequence of propositions, like a whole stack of donuts, not donuts, dominoes, one for each n. Now the technique used in mathematical induction is to prove the first statement in the sequence and then prove that if any particular statement is true, the one after is also true. That is, the dominoes are spaced such that the knocking over the nth domino knocks over the n plus first domino. This enables us to conclude that all the statements are true. Now let's state this in a more formal language. So we have an initial step where we prove the proposition is true for n equal 1. Or if the assertion is true for some n equal k, we'll prove it for n equal, well, I said k, n bigger than or equal to a, we prove it for the first domino, or n equal a. Then we have what is called an inductive step, where we prove that if the proposition is true for n equal k, then it must also be true for n equal k plus 1. This is the dominoes being spaced in the appropriate way. This step is the difficult part and may help if we break it into several stages. So anyway, stage 1, we write down what the proposition means for n equal k. This is what you're going to assume, that's the if part. It is often called the inductive hypothesis. But then we write down what the proposition asserts for the case n equal k plus 1. This is what you have to prove. Keep this clearly in mind as you go. And stage 3, we want to prove that the statement in 2 is true, and we almost always will use the statement or the assumption in stage 1. Now there's no real recipe for how to do this. It'll vary from problem to problem depending on the mathematical content, and sometimes you have to use your ingenuity, common sense, and knowledge of mathematics here. The key question is, how do I get from stage 1 to stage 2? Once the initial and the inductive steps have been carried out, we conclude immediately that the proposition is true for all n greater than 1, or for all n greater than or equal to a if we started at n equal a. Okay, to explain this, it may help to think of this as an automatic statement proving machine. We proved it for n equal 1 by the inductive step. It is true for n equal 1, but it's also true for n equal 2. And again, it is true for n equal 2, then it's true for n equal 3, and so on and so forth. Because we approved the inductive step, the process will continue and will never come to an end. So this machine runs forever. And in fact, if there was a number, capital N, for which the statement was false, when we got to n minus 1, it wouldn't work, and so that's what happens. And if you think about this being computer programming, this would be like a loop, but instead of being like a computer where the loop will not run forever, this one does. Okay, so let's see how this works in practice by proving our proposition. So proposition 1, you may recall, is that the sum of the first n positive integers is 1/2 n times n plus 1. Now our initial state is if n equal 1, then n equal 1 and 1/2 times n plus 1 is 1. So you see the result is true for n equal 1. Now in our inductive step, we're going to make an assumption, and that is called the inductive hypothesis, and that asserts that this is true for k. In other words, 1 plus 2 plus 3 plus ... plus k is equal to 1/2 k times k plus 1. We assume that this is true. But now we want to prove that it's true for k plus 1. That is, we need to prove that 1 plus 2 plus 3 plus ... plus k plus 1 is 1/2 times k plus 1. That's what n is now, and this is k plus 1 plus 1, and that'll be 1/2 k plus 1 times k plus 2. Okay, so the question is, how do we get from stage 2 from stage 1? Well, the answer here is that we start with the left-hand side of stage 2, which is right here. It is 1 plus 2 plus 3 plus all the way up to n k plus 1. But now we write that in this way, and here was k plus 1, but this was k. So you see, my dear students, we can use the induction hypothesis on this. This is subtle, so make sure you understand this. So this first part, not counting the last term, is, by our inductive hypothesis, 1/2 k times k plus 1, plus k plus 1. But here, you see, there's a common factor of k plus 1, which I can factor out. So when I factor out k plus 1, I will get k plus 1. This is going to be 1/2 k, and that is plus 1. But you see, whenever I pull this, whenever I simplify this, algebraically, this is the same thing as 1/2 times k plus 1 times k plus 2. This is what I needed. This completes our inductive step, and the result is true for all n bigger than or equal to 1. Now, let's talk about, as a further example, let's try proving proposition 2. And that's a little more complicated. That says the number of diagonals of a complex polygon with n vertices is 1/2 n times n minus 3 for n bigger than or equal to 4. So for our initial step, we're going to be looking at n equal 4. And so this means that there are 4 vertices. This is a quadrilateral, and there are 2 diagonals that you can see. And so if you take n to be 4, then the formula that we're trying to prove, 1/2 n times n minus 3, is equal to 2. So you see it is true for n equal 4. So we've shown that. Now for stage 1 on our inductive step, we're asserting that, and we're assuming, this is the hypothesis, that the number of diagonals of a polygon with k vertices is 1/2 k times k minus 3. And we want to prove that the number of diagonals of a polygon with k plus 1 vertices is 1/2 k plus 1 times k plus 1 whole minus 3, which is simplified into this expression. So how do we get from stage 2 from stage 1? And the answer is we add another vertices. Okay, so let's do that and see how we can count the additional diagonals that can be drawn as a result. And figure 3 will help. So here is the polygon with k vertices. And again, we're labeling those P1 through P sub k. And we add a piece of k plus 1. Now, where we're adding it is up here, and this becomes a polygon with k plus 1 vertices. And so we're going to count the number that we have here. So when we add an extra vertex to the polygon within vertices, all the lines which were diagonals of the original problem will still be diagonals of the new one. And the hypothesis says that there are 1/2 times k minus 3 existing diagonals. In addition, new diagonals can be drawn from the extra vertex P sub k plus 1 to all the vertices except the 2 adjoining P1 and Pk. That gives us k minus 2 extra diagonals. Finally, joining the line P1 and Pk, which used to be a side of the polygon, is now a diagonal. That gives us a total of 1/2 k times k minus 3 plus k minus 2 plus 1 diagonal. But when we look at the algebra, we see that 1/2 k times k minus 3 plus k minus 2 plus 1 can be shown to be equal to 1/2 k plus 1 times k plus 2. That completes the inductive step, and hence the result is true for all n greater than or equal to 4. Now at this point, it's a good idea to go back and read over the explanation of the process of math induction, thinking about the general explanation in light of the 2 examples we just completed. But now we're going to do something more complicated. We're going to illustrate the process again using math induction, giving a proof of an important result. We've been studying this in class, which is frequently used in algebra, calculus, probability, and other topics, including discrete math and graph theory. And it's the binomial theorem. The binomial theorem states that if n is an integer greater than 0, then x plus a whole to the n is x to the n plus n, x to the n minus 1a, and this is n minus 1 over n times n minus 1 all over 2 factorial. This is x to the n minus 2a squared, and so on and so forth. Again, this is the binomial theorem that we've covered in class, and we have statements for how to obtain these coefficients from either Pascal's triangle or from the binomial coefficient formula. Okay, so we're going to prove that, and it's more compactly expressed this way. X plus a whole to the n is a summation from n equals 0 to n of n. Choose r, x to the r, a to the n minus r. Okay, so we're going to prove this by induction. Well, our initial step is, what happens if n equal 1? Well, certainly x plus a to the 1 is equal to x to the 1 plus a to the 1. That was not algebra there, but that's true, and that's equal to x plus a. It'll be a different thing whenever we do k. But now, this was our initial step. So you see the first domino has Now, our inductive step, we're going to assume the theorem is true for n equal k. That is, we're assuming that this is true. So now we want to prove that the theorem is true for n equal k plus 1. Now, please note, my dear student, we need to show that x plus a whole to the k plus 1 is this expression. Make sure you understand the expression that we're looking at. So we're going to algebra. So we look at the left-hand side of that equation, and we observe that x plus a whole to the k plus 1 is x plus a times x plus a whole to the k. But our inductive hypothesis says that this part is all of this. So what we're doing is we distribute twice, and when we do the distribution here, and again you should verify this, we will get this expression distributing first the x, and then we will distribute the a starting here. But when we add those, we get this expression, and this is the right-hand side as required. Hence, this result is true for all n bigger than or equal to 1. You should follow carefully and make sure you understand each of these steps. Here's another problem that I would suggest that maybe you try for yourself. The sum of the first n odd numbers is n squared. So give it a go, please. Let's see how you... Well, step 1 is certainly true because the sum of 1 is 1 squared. So we make our inductive hypothesis, which says that 1 plus 3 plus 5 plus ... going up to the nth odd number, which is 2 to the n minus 1 is equal to n squared. Okay, now we want to prove that the sum of the first n plus 1 odd integers is n plus 1 whole squared. So how do we get from stage 2 from stage 1? Well, the sum of the first n plus 1 odd numbers is the sum of the first n plus 1 more. And so we take this and this. But now we're going to use inductive hypothesis on this part, so that is n squared plus 2n plus 1. But that is simply, algebraically, n plus 1 whole squared. Therefore, this result is true for all n bigger than or equal to 1. Now, finding the formula, though, is a hard part, and this is an important part of mathematics. This is a different and bigger problem for real mathematicians. They look at examples, but then they use induction to prove it. So again, math induction, a great tool, but not a panacea. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself, because self-care is important. And now more than ever, take care of each other, because we're all in this together. Look forward to seeing you in class. God bless you all.